Thank you very much to the organizers for inviting me, and thank you to all of you who I recognize and spent time with. It did feel a little bit like coming home. I did live here for a few years, about a decade ago, and honestly, the temperature of the stage makes me feel even more at home. Yes, thank you very much for that. I had a good conversation with Sir Peter Knight, actually, and you've put together a wonderful program, and I'm his counterpart for the Canadian National Quantum Strategy, but I'm not going to be talking to you today about everything that Canada's up to in terms of its national quantum strategy, other than to say I think there's pretty good alignment between all the Five Eyes on the importance of this and the importance of commercializing a branch of physics. I think we all recognize that if you map it back to even what the last commercialization of a branch of physics looked like, it was the commercialization of semiconductor physics. And Peter reminded me that the Colossus system, like the vacuum tube system, the applications weren't well known back then either. They were thinking about code breaking, and they were thinking about ballistic projections. So the fact that people weren't thinking about Facebook, or they weren't thinking about AI, and a lot of these things come through, yes, once you're able to build on top of existing scalable systems, and then you can start playing with things like heuristics. We're not quite there yet, and what I would like to speak to you today about is kind of a working backwards approach, because there's a lot, when you talk about industry, and you talk about industry deployments of quantum, there's this kind of bottom-up approach that is naturally occurring. And I think it's important to take a step back and take a look at, okay, what are these known aspirations, these known high-value applications, and what will it take to actually build that, right? Rather than doing the bottom-up approach and trying to find value with the small-scale systems that we have. I think the point taken on the previous panel is it's a fantastic one. What we're looking for those known applications, those deterministic ones, Shor's algorithm or chemistry or the rest, those are like moonshots. And we shouldn't be trying to hit a moonshot by building ever taller ladders. We need to take a moment and think about what does it look like to engineer a system capable of that kind of value. Because of course, once we unlock that kind of value, all the rest will come. And then we're all going to do very, very well. Because in some sense, you can tell that we are here before quantum was cool. And the reason you can tell is because this is a room full of suppliers, not users, right? That will change, but we have to take a serious look at what it's going to take to build something that will deliver that kind of value. And so it's a bit of a working backwards approach, and I'm going to introduce a few different concepts that frankly are to some level independent of what the underlying technology is. It's kind of driving to some conclusions that I think people can borrow from. And then towards the back half, if I do have time and I don't go nattering on about architecture too much, I'll share with you a little bit about the progress that we're making towards that vision. But I think it's more important to talk about some of the key concepts that I think, honestly, we've been missing for 20 years. So it's only kind of shifting right now in the conversation to think about, okay, what does it mean to do systems engineering for quantum? And there's some it seems kind of obvious once we put a few things together, so at least to me. So hopefully I can spend some time with you and work through some of that. I'm going to introduce, and not the first to introduce, but I really do think that it's important to think about quantum computing in multiple phases of its technological development. There are certainly, you've heard the term NISQ, and I think that is an extremely important first phase of quantum technologies, where the criteria is more about, okay, what kind of qubit count can you get? And it's been this early, really interesting phase where people didn't know a priori if there was going to be commercial value. This noisy phase before there's error correction. There will, following from that, be a phase 2. And this phase 2 will be when you have single modules with error correction to some level. And the concern that I have, and the concern that a lot of people had with the NISQ phase, is people started saying these words like quantum winter, because a priori it wasn't known if there was going to be heuristic value in that phase. It was totally reasonable to go try. But seeing not as many end users in this kind of conference right now tells you kind of where that's landed so far, which is not to say that it won't eventually provide value, potentially. But my concern is that actually even in phase 2, we'll have that same situation. That we'll have small-scale, fault-tolerant, single-unit systems that won't be able to do much of commercial value, right? Even if you had a couple hundred logical qubits with okay logical error rates, it might not be cost-effective enough or useful enough for people. What we're talking about for phase 3 is what I would call networked quantum computing. And this is where it is true that commercial value can live, because once you're working with networked or distributed quantum systems, you can rack mount and put them together and put as many resources down as you want. And to some level, all of the applications that we've been talking about, if we're talking about the chemistry applications or Shor's applications or those other ones, requiring the kind of thousands of qubit level, maybe hundreds to thousands of logical qubits, all with pretty impressive logical error rates, right? We've heard the number 20 million on the stage right before me. I disagree with that number, and I'll get to in a moment about that, but it's still a large number. And for all of these systems, you have to do error correction. You have to hit such a degree of environmental perfection that at some point, the box itself is going to be containing only it's easier to start putting boxes together than to try and squeeze more into any one environment and keep that control to that exact exquisite precision needed for error correction. So it will be very interesting to see how this changes, because we're moving. It's really phenomenal. We're shifting from this NISQ phase, and that's why you can feel the excitement again. And people stopped talking about quantum winter for the past 2 months a little bit, which is great, because they're excited. Oh my gosh, we have fault tolerance, there's these error correction demonstrations. Finally, we've arrived. But what I'm here to share is that I don't think that's quite cracked it yet. I think we really have to be designing for phase 3, networked quantum computing. And the problem with going headstrong into phase 2 only and thinking only about how many things you can fit into one box, there's a few proposals that can get quite a number into any one box. I appreciate that. But at some point, because of the space-time trade-offs that you get with these algorithms, with all of these algorithms, more will always be better. So at some point, phase 3 will win out, right? Especially the most powerful quantum computers, the highest value, big applications, those will be on a networked system at some point. All right? So I still think it's an open question. Maybe there's going to be excellent heuristics that come out of phase 2, and I want that to be true. I think that'd be fantastic. But we have to keep in mind what the system design requirements are for phase 3, because that is where it really will click in, right? For all of us, it will really click in. And I'll tell you that what you get in phase 3, if you actually think about what you do for system design for phase 3, it's building the rocket ship. It's not an ever taller ladder. You have to go to the very basics of what you're trying to do, and your priorities actually shift. So instead of constantly talking about C0 fidelity, it's about entanglement distribution. And we'll get to that. So, I mean, there's going to be different players that work in all of these phases, and I think everybody, honestly, I'm a little bit more optimistic than most. I think there's going to be lots of different platforms that can eventually deliver value in more than one of these phases. But I think ultimately, if you're going to compete on performance, what I'm suggesting is that there's a certain set of metrics that we should all be thinking about to really compete and really deliver value for phase 3. Okay, so if you're going to think about phase 3, let's just take a priori, the picture that you're going to have chemistry or factoring algorithms distributed across multiple computers. How much logic do you think can happen within a module versus between modules? If you were to run a Shor's algorithm, how much of the logic is in between boxes rather than within a box? The fact that we don't know the answer to this question off the top of our heads actually tells us quite a bit. And for some applications, you actually need a lot of logic in between boxes. And for some applications, you don't. So again, very early data I'll share with you here, but we just asked that very basic question. Well, how much logic do you need? Because that tells you what the bottleneck of your total system performance is. If you go and you take a look at classical supercomputers, which are horizontally scalable, right? Rack-mounted, put them all together, the performance of inside a box is almost irrelevant compared to the performance linking these systems together. That is the thing that dictates the performance of these systems. So we ran some calculations, and I'll walk you through it, just really briefly, just to kind of give a sketch of it, if you were to run Shor's algorithm, unless you actually do a lot of innovation, the fraction of gates, the fraction of logic that you have to do in between modules is almost all of it. You can, fortunately for Shor's algorithm in particular, really work at that. You can really crack it down and down to a couple %. But that's saying if your intermodule logic is more than 20 times as expensive, you're in trouble. For chemistry, which should be the higher volume applications from a commercial perspective, right? There'll be some market for Shor's algorithm, but much bigger market for the chemistry, pharmaceutical, material design side, right? If you take a look at that, again, these are just kind of first estimates, but if you take a look at that, the fraction of the logic that you have to do between modules can be over half for very reasonable module sizes. So we're in a situation where people are talking about, okay, what's your logical clock cycle? And I come back, what is your intermodule logical clock cycle? That's the one that you should care about. And if you can make that as fast as everything else, then you're in a good spot. If that's the expensive part of your box, you're in trouble from a systems engineering perspective. Okay, so let's just try to motivate the scale of it. It gets worse than that when you start to think about how logic works between boxes. So again, forgive me for making this like rather technical, but it's kind of trying to drive home the point. We've been trying to optimize for maybe the wrong thing, right? We've been trying to optimize for, okay, well, what's the 2-qubit? Like, we should be really thinking about entanglement distribution, because that is what this is. Everything about intermodule logic is entanglement distribution. And so we should be optimizing for that. And that gives rise to the performance of a large-scale system, as well as the commercial value that we all want, so that we can all leverage this commercialization of the next branch of physics. Okay, so I decided to come up, and this is Steph's lessons, all right? So I'm not speaking on behalf of Canada, or I'm not speaking on behalf of, I just came up with a few, like, we've been thinking about this from a systems engineering perspective. And there's an axiom here. So the first one is that, okay, I'm just gonna take as given that at some point we're gonna need to horizontally scale these things. So I just put together a few lessons to kind of think about it. You could take them or leave them, right? So they're not saying they're rules or anything. But if we want unlimited horizontal scaling, okay, we're going to want modularity. I've already made the case for that point. But lesson 2, let's take a look at what that actually means, okay? Because if you're going to be, and I'll walk through each of these in a little bit more detail, but if you take a look at how you actually implement logic in an error-corrected system, it really isn't sufficient just to stick a transduction element on the edge of your system. If you wanted to do a logical operation between two error correction blocks, if you wanted to do like a logical bell pair between two different modules, you actually need physical bell pairs. And the better your code means the more bell pairs you need. So if we're talking about most of your logic being in between modules, you actually, in the ideal case, need an I/O, an optical I/O, in the ideal case, between all of your physical qubits in every module. Right? That's a system design aspect that changes exactly. Like that means you're not talking about, oh, is it milli-K or is it what? You have to be thinking about the I/O, the quantum I/O, the entanglement I/O for every single one of your qubits. And if you don't, the overheads are massive for just the entanglement distribution part. When you take a look at that 20 million number for Shor's algorithm, none of that includes the entanglement distribution cost. And the few papers in that space that are taking a look at entanglement distribution have overheads of like 90 to 95% of the computer its entire job is entanglement distribution. Right? So this is a bit of an elephant in the room that a lot of people aren't wanting to talk about, but if you take it head on, it actually leads to some beautiful, beautiful conclusions. So, okay, let's take as given that we have an optical I/O. In that case, in the ideal case, that we have an optical I/O per qubit. That'd be great. Okay, wonderful. Photons get lost. There's really no way around it. Even the best photons get lost. And by best, I mean telecom. That's the lowest loss components, the cheapest components. They still get lost, right? So if you're going to make every single photon count, the collection efficiency, you gotta capture every photon you can, which again changes what kind of initial key criteria you want.
You want to be working with something that is ideally in the low loss bands, ideally. You can collect all of it, right? And you're going to want to have lots of I/O for your system. So that's one of the lessons that we're working with, and I'll speak to that a bit. Okay, but here's the good part. If you have an optical I/O for each of your qubits, you don't care what the planar connectivity is. Okay, why does that matter? If you have the ability to link qubits through an I/O port per qubit, you can connect them any way you want, which means you're not stuck with horrible codes with horrible overheads. So maybe just as an interest, how many people are familiar with LDPC codes? Okay, a little bit. For those of you who are in the audience, if you're interested in quantum, this has just changed your lives. This has completely changed your lives because it's made realistic value like 20 years closer, because we're no longer stuck with horrible overheads with the planar codes that we have. If you have this circumstance where you're working with modular connections, that means you can connect these things any way you want, which means you can use these amazing codes. Just amazing codes. And these codes are so amazing that the suppliers, some of the suppliers that have nearest neighbor connections only, are specifically engineering entirely new designs for their systems just because these codes are so good, right? So superconducting systems are like, you already have people saying, these codes are just so amazing. So you get this for free by thinking about modular interconnections. And so that's the point about lesson 4, is that connectivity has been this massively underappreciated system engineering perspective for quantum. For 20 years, nobody really talked about how important connectivity is. Connectivity takes those overheads of like 3,000 physical qubits for one logical qubit down to 10. Down to 10. So why aren't we designing for the best codes that are out there, right? Why don't we work backwards from success and figure out what that means for the systems? I'll walk through each of these in a little bit more detail. I'm sorry. I could get really carried away with all of this, but I wanted to just say, hey, if you have these, just to reemphasize this point, if you have connectivity between any of your modules and you can connect them any way you want, you don't care about the planar connectivity at all. You get whatever connectivity you design into your system, and you could design it for the best error-correcting codes as possible. But I would say that this is true regardless of what system you have. You're always going to have some box, right? Whether or not it's a chip or it's a vacuum chamber or whatever it is, you're going to have to think about that and maximize. And then you can get cost effectiveness. That's the other thing people aren't really talking about yet. Cost effectiveness for these systems, because once you can modularize, you can duplicate and then just get a better cost base per logical qubit. This is what I meant about the importance of the quantity of the I/O. So let's, for a moment, imagine you have an ion trap with as many 9s as you possibly want, and you have 2 different modules, and perhaps it's a CSS code here. I'm just, again, trying to maybe a little bit more detail, but just to illustrate. For case A, oh, sorry? Thank you. For case A, if you only had a transduction or an interconnect tacked on the edge, and you use that to do your entanglement distribution, you're kind of in trouble, because the logical gate, if you wanted to have the logical qubit on one side talk to the logical qubit on the other side, it actually requires pairwise entanglement distribution for each of the pieces. Whereas if you have I/O for each of your qubits, then you can get it in one step. So the time overhead goes way down. And this gets back to the original point, what kind of slowdown do you expect for intermodule operations? So if you have the high connectivity situation where each of your qubits has an optical I/O for the ability to do entanglement distribution, then you can do that logical C0 operation between those 2 logical qubits in a single step. Whereas if you have an interconnect right off to the side, the overhead just blows up, and that's even assuming all-to-all connectivity within your systems. Right? So this gets really scary really fast. I can completely understand why people have been sweeping it under the rug, but it's a really core challenge between here and value, so we should really be tackling it head on. And this gets worse, of course, if your overheads get higher, but I just wanted to use this as an illustration. So what I'll talk to you about in the back half of this conversation is our implementation of this vision, right? So we're working on what's called the T-Center, but honestly, Any spin photon interface works with these narratives, right? So whether or not it's a vacuum tube, Colossus-style spin photon interface, or a solid-state one, here we're using silicon, it's a telecom band interface. Honestly, these things can all work with this kind of model, and we should be thinking about that systems engineering under that perspective. The reason why I'm most excited about this one is I think it's prime for entanglement distribution. So it's right in silicon. It is, and silicon photonics is the thing you want to do to be doing distribution of photons in a chip. It works very comfortably at 1 Kelvin, and of course it's natively at telecom, so you have all those low-loss components. Okay, and I spoke to this a little bit about the LDPC codes. I would say overheads of 20 to 1 are perfectly reasonable, and people are working really hard at the long distance to try and make this plausible, but they're very, very exciting codes. So what does this look like if you put it all together? You have some kind of modular construction where you have, for us as a cryostat, 1 Kelvin. On the photonic chip, you have qubits, each of them with their own I/O port, each of them telecom linked, lots of fiber I/O coming out. On the chip, you could distribute the entanglement locally, however you like. Again, photons can route quite naturally. Detectors and switches all on chip. And interestingly, and I'll shift to this now, this is exactly what you need for a scalable quantum network. Okay? So let me speak to that for a second. The thing that has been blocking quantum networks is also scale, but a different kind of scale. They're missing the scale of user count, and they're missing the scale of total distance. If we were thinking about what is going to unlock networks, it's actually repeaters or hub-spoke networks for user count scaling, and that is, to some level, a small quantum computer. So the very thing that we've been talking about that unlocks scalability for quantum computers is really thinking about it as a network of qubits, right? If all of your qubits have I/O ports, it's essentially a giant network of qubits that are all in together. That gives you scalability for quantum computers. It unblocks this kind of box limitation. But similarly, the networked computing is what unlocks networks by having repeaters be the exact same fabric, the exact same physical technology. And so I'm completely of the opinion that quantum networks and quantum computers are the same technology in the limiting case. These are the same thing. And for any technology that tries to accomplish one without the other, it'll be difficult to compete in the limiting case with a technology that can operate in both regimes. So let me just go through a bit of physics, and then I'll show up some really, really fast results right at the end, but just to show you how it looks. So regardless of your spin photon interface, you want to put it into some kind of optical cavity. That is just so that you get all that light, right? You're trying to capture all of that light for entanglement distribution. How do you get the light and entangle these things together? So for us, again, getting a little bit more detailed, but you can put these things into silicon photonic cavities, but of course there's free space cavities that can do the same kind of work. We can spin entangle the photons. So what we do is we have these spins, gorgeous, gorgeous qubit properties, right? So we set, I was part of the team that set the 3-hour coherence time record before we were beaten for the 6-hour coherence time record a little bit later, using these spins in silicon. Spins in silicon, I mean, I'm talking to an Australian audience. I shouldn't have to talk about how great these things are. Everybody knows. But they have good photonic properties too. So you can take a look at that, and then you can create, on demand, a photon that's entangled with the spin it leaves behind. Then what you do is you can get these things to interfere with one another. It's an HOM measurement that can characterize the quality of the entanglement that you can put into the spins that are left behind. So once it's in a photon, the photons can go anywhere. Photons are great room temperature qubits, so you can route them all over. And actually, the T-centers, generating entanglement between T-centers, they don't care if they're next to one another or if they're across the room. So long as they're part of that same telecom network, you can generate entanglement between them. And that's, from a scaling perspective, so, so nice. Because then, actually, your yields aren't a big issue, right? And crosstalk doesn't get worse as your system gets bigger. You can just keep these things nice and spaced out, and you don't need to worry about it. So the one mechanism for generating entanglement using these photons is what's called a Barrett-Cock protocol, but honestly, there's lots of different protocols that you can go take a look at. I like this one because it has the ultimate performance of fidelity without having to do any massive phase stabilization. So that's a bit of a detail. But yeah, what you can do is you can generate entanglement. People think C0 gates are the necessary universal gate, but it's really the entanglement. Once you get entanglement, you can consume that entanglement to do a teleported operation, a teleported gate, or to consume it to do any of the, so you can replace C0s with just complete bell pair distribution, and everything from a universality perspective is right there. And given that entanglement distribution is the key to modular computing, I think that should be the basis for how we compare fidelities of our system. What's the fidelity of your bell pair? Okay, and I said this works for networks. You can use this exact same network for whatever networking application you have. So you can have room temperature, essentially not so dissimilar from a transceiver, sending single photon signals into one of these hubs to use for any of your QKD applications as well, right? You can load your user qubit with a photon, room temperature, into a T-center by using the exact same interference physics. And then from there, they can do entanglement distribution to any of your other nodes. So now we actually have a network that is physically scalable. This is what a repeater is, but also scalable in terms of user count. Any user that plugs into your system can connect into this network. So that means for blind computing, QKD, any of those. And it's going to be super fascinating to see what the market how the market thinks about quantum networks as Shor's algorithm becomes more realistic and in line with a modular distribution system. So that's the kind of architecture side. I have apparently 3.5 minutes to run through some of the physics. So for some of you, if you're into this, you'll get what I'm talking about. And if nothing, if you guys aren't into the physics of it, then I mean, this is just for the people who have made it this far. I'll give you some of those details. But I would say that maybe what I can share, I am a professor at Simon Fraser University, and I'm also running Photonic Inc. Photonic Inc. We have 130 people working on this, and worldwide, and about half of them live in Metro Vancouver. And some of the results I'll just flash up quickly on the screen here. You guys are some of the first to see it. We haven't published this stuff yet. We've been quite quiet about it. Share a little bit, but some of the results are from the research effort up at the university, and some of them are from the development effort at the company. So I'll skip through some of this, or I'm not going to go to the details of it, but I'll just share. There's a lot of modeling, clearly, that goes into this because we need to understand these defects and their capabilities because you want the ultimate levels of entanglement distribution and performance. So fortunately, we can already say that we can overcome a lot of the manufacturing variability you would expect in a silicon thing. We can tune these things up. We know a lot about the details of the transition. OK, great. Those details are to come. I would share that one of the things that seems to bother some of the color centers in solids is that you have this natural dephasing process that happens when you do an optical excitation. Fortunately for T-centers, we can avoid that by working at these very specific points where you have these zero dephasing points. So the nuclear spin can stay nice and happy through multiple optical excitations without any intrinsic trade-offs. So that allows for high fidelity operation in the limiting case, which was very exciting. We have 3 nuclear spins in the T-center, so you can use that for local computation as well as the electron that you use to do the entanglement distribution. So lots of details there too. Oh, I just got added 6 minutes. Was the time? Oh, okay. Well, sure. All right, I'll just throw more opinions down. All right, fine. Okay, so one of the nice things about silicon is you can print as many as you want. So I did it just for the sake of it, but 3 years ago, I printed a 1 million qubit chip just to have it. So if you want to, I carry it around with me in my purse, honestly. So if you want to come take a look at it, you can. But what you can see is that like the qubits themselves won't be the footprint issue. And fortunately, for 1 million, you could even print 1 million and pick your favorite 100,000. Right? So when you have something where you don't worry about local connectivity, you can work in a much more mass manufacturing sense. So what we did here, I'll just show you some of the little results we have. Again, we haven't shown any of this out there, so people might not know that we're able to do that kind of stuff yet, but you can do these I/O ports. So if you take a look at the top left there, that's an optical I/O port. If you put like a fiber down on top, you can get pretty high collection efficiencies through that. You can get like 90%. And each one of those goes and talks to a qubit. So the qubits you can't see. They're atomic in scale. They're half a nanometer. So the actual infrastructure that you have on the chip, which will determine the qubit count ultimately, are all the photonics, not the qubits. So the qubits themselves are going to be really, really tiny. But you're going to have to do that kind of tuning for them and put that down, and that's OK. So with that, we put them into cavities. Cavities allow you to collect all the light, so upwards of 85% collection efficiency out of the qubit and into the fiber and into your system. We can do G2 measurements, and we can get good per cell. So per cell tells you, how well it's coupled into that one mode. And so if you want to collect every single one of those photons, we have here per cell on the order of like 20 or so, or a lifetime reduction on the order of 20, which means you're collecting almost all that light. So really, that is going to be the metric. Because remember, when you're thinking about entanglement, it's just a bit different than a CNOT gate. Because if you're thinking about entanglement distribution, you can distill it. You can distill it. So you want to get the entanglement there, and you can tell what quality of entanglement you get, and then you can choose to keep it, or you could choose to distill it into a higher quality. So really, it's entanglement management which is going to determine the performance of these large-scale systems. So all of these details go into that. And so, yeah, what you do is you put these T-centers right into the middle of cavities, and you can collect all that. So we're working a lot on yields and reliability and variability, and it all is very, very fun. And so the last one I'll show you is kind of a sneak peek of some results that we'll be sharing later on, but taking a look at interference between these things. So, okay, how good can you get entanglement between these? What you're looking at, you take them and you get the qubit frequencies to overlap. Okay, so they have to be indistinguishable. This is true. If you're not familiar with these spin-photon interfaces, that's how you get the entanglement. You get indistinguishable photons that interfere, all right? When you get that interference, you can characterize it with what's called an HOM measurement. And you could take a look at here on the right, and you can show that for certain time windows, you can get very, very high fidelities. And what we've seen for some time windows is that these fidelities can get upper bounded by about 93%, and that's just our first go. This is the early results that we collected a little while ago. So yeah, clearly work to be done, but I would say that we found these qubits about 4 years ago, so it's moving really, really fast. And the scale that you get by working with silicon and telecom color centers is a good place to be, because you don't need to just think about modularization, but you need to think about also, of course, how many qubits you can fit into any one box. So those are the kinds of things that we have going on. There's a lot more going on. We are a full stack company. There's a lot on the algorithm design and on the LDPC, decoding, compiling, quite a bit of work there, and a lot of engineering. So it's a lot of fun, but I think if we're working backwards from success and you're just heads down on what matters most to deliver value, then we can cross that line, we can cross that chasm, and bring these things online for everybody as quickly as possible. So with that, I'd like to, oh, I have one last one. Okay, fine. Good. Okay, so one last one. We also have maybe some spin control, we do have some spin control work to share as well. So if you take a look at when you do these interference measurements, you can also take a look at the spin control as well. So what you're looking at is one of our chips from, a few years back now. The blue section is the optical I/O. The qubits are what you're pointing at with those yellow electrodes. And so with there, you can characterize the spins. So we have really high fidelity single qubit data, as you would expect. These are spins in silicon. They're not so different from phosphorus, to be honest. They just have a few more nuclear spins that you can play with. The nuclear spin Robbies look pretty good, too. And our readout, we can get a very good single-shot readout for both the electron and the nuclear spin. So all of those kinds of flags will be waived in due course, but it's just a little sneak preview. And with that, I'd like to thank you.